if you think about why a science like economics or even something like evolutionary biology took the route that they took in terms of being reductionistic, linear, and so forth, basically it's because if you try to imagine, somehow create a model, try to look at the world by analyzing it in this kind of holistic way where agents are interrelated, are communicating to each other, where the whole is not equal to the sum of its parts because precisely of this interaction, the mathematics of that becomes intractable is the word. It basically becomes impossible. So we could not have enough blackboards in your university to write down all of the equations that you would need to describe how the system is behaving, right? So there's a phrase that I really like in nonlinear complexity thinking, which is the algorithm is the solution. In the sense that if you're trying to ask a complicated question about, hey, I have this agent here and it's doing something, what's going to be the effect on this other agent here? You really have to see how that agent is affecting and affected throughout the system to see it over here, and there's really no way of reducing it. Talking about things like, for example, neural networks. I co-wrote a paper with a colleague of mine in the engineering department in which I didn't know much about neural networks. He was an expert in it, and he was trying to see if you could use neural networks to predict things like financial time series, right? So I grabbed a financial time series that was really, really well studied, right? And I did everything that had been done about this financial series, trying to predict how much an economy is going to grow in the future. And I, basically had my econometrics package, and I did all kinds of regressions of that, like all of the state-of-the-art econometrics techniques to try to see if I could extract all linear information out of that. If you think about a multiple regression, what are you doing? You're trying to explain one variable in terms of other variables, but you are dissecting the system such that you have just, this variable only affecting things in that particular way, and ultimately you want to have that variable next to a coefficient that says, hey, when this variable goes up, the coefficient is negative, so this variable of interest is going to go down. That's how you want it, right? And so then we analyze this series both in this kind of linear traditional way, and then my colleague used a neural network to analyze it, and then we were seeing that there were some things where the neural network really helped us predict much more what was going on. So I got really excited. It was, wow, this neural network, which you can imagine is basically a generalized nonlinear regression, right? So if you give enough degrees of freedom to the neural network, you can basically write your name, right? You can describe anything. The neural network, in some sense, can basically memorize the data that you have. So you have to be careful of that. But he was very careful in trying to generalize the kind of results that we were seeing. Once this was really well calibrated, it was still, in some time series, predicting much more of the results than my linear approach. So immediately I went to him and tried to get a story out of it. So what is the neural network telling me that the linear regression cannot tell me? And the answer was, I can't tell you, right? It's exactly that part that is nonlinear that you can't really turn into our traditional way of thinking of when this variable goes up, this other variable is going to go down.